Hey, and welcome back to our AP Chemistry flipped classroom where we're beginning our introduction to equilibrium. So this is the 7th unit of AP Chem. We're more than 2/3 of the way there. And so we're going to start with chemical equilibrium. You'll hear me talk about the law of mass action as well as the chemical equilibrium constant. So the law of mass action, which we'll call the equilibrium constant, was developed by Cato Maximilian Goldberg and his brother-in-law, Peter Veig. It's been around for a while, and I think you'll be pretty comfortable with the concept. So let's go ahead and jump in. So before we can start talking about the law of mass action or that equilibrium constant, we really need to talk about the two different kinds of reactions that can happen in chemistry. The ones that we're most familiar with are those one-way reactions. These are reactions that go to completion, and these are the ones that we talk about most of the time. So I've given you an example here, sodium hydroxide. When it's solid, if we drop it into water, it completely dissociates into those sodium ions and hydroxide ions. We could also think about a combustion reaction when I have some propane and I combine it with oxygen and provide it with activation energy, then it completely burns and we produce carbon dioxide and water, and there's none of the original reactants left. So that's a pretty typical chemical reaction. The other kind of a chemical reaction is a reversible reaction, and most specifically, an equilibrium reaction. So when we talk about an equilibrium reaction, we're talking about two opposite reactions that occur at the same time, the forward reaction and the reverse reaction. So we'll go through a few examples of types of reversible or equilibrium reactions. The first one we're going to talk about is a dimerization reaction. There are a lot of dimerization reactions in chemistry, and many of them are reversible and temperature dependent. So we have this example where we have nitrogen dioxide, and if we have two molecules of nitrogen dioxide, they can come together and form dinitrogen tetroxide. And this is a reversible reaction. So we can see that this is temperature dependent. Dinitrogen tetroxide is clear. Nitrogen dioxide is brown. You might remember that because you produced it in the copper lab when you dissolved the screw in the concentrated acid. And so what we can see is that this reaction goes back and forth. It produces nitrogen dioxide, it produces dinitrogen tetroxide. If we change the temperature, we can change the ratio of those, and we'll talk about those more in a little bit. But you can actually see this reaction going back and forth. Another good example of a type of reversible reaction or an equilibrium reaction is the dissociation of a weak electrolyte. Remember, we've talked about the fact that a weak acid does not dissociate completely when dissolved in water, but only part way. And so here we have acetic acid and water, and we see them coming together to make the acetate ion and the hydronium ion. And this reaction goes back and forth, and producing the acetate ion and the hydronium ion and acetic acid and water at the same rate. And we'll talk about that because that rate matters a lot with equilibrium. And then the third example that we're going to talk about is saturated aqueous solutions. So we know our solubility rules. We know that certain things are soluble and certain things aren't soluble. And so if I asked you, you would tell me that silver chloride is not soluble. But the fact remains that when we put silver chloride into water, a teeny tiny fraction of it does dissolve and dissociate. And so we'll have mostly solid sodium chloride, but we'll also, silver chloride, but we'll also have a few silver ions and a few chloride ions. And those silver ions and chloride ions are going to be bumping into each other and making solid silver chloride, and the silver chloride solid is going to be very slowly dissociating into silver ions and chloride ions. So both reactions are happening at the same time. And something we might be a little bit more familiar with is sugar dissolving into water. And we know that sugar dissolves into water, but we also know that if the water's cold, it doesn't dissolve very well. If you think about trying to stir a spoonful of sugar into iced tea, it doesn't dissolve very well. And you can keep adding sugar, but it's still not going to dissolve. And so we have that same sort of a situation where you have the solid sugar sitting on the bottom and some sugar dissolving into the water. But that process is that some of it is going to dissolve and some of it is going to precipitate back out. So our definitions of chemical equilibrium. A reversible reaction is a chemical reaction in which the products can react to reform the reactants. So all three of the examples we've been talking about, the products can react and reform the reactants. If we go back to that original example at the beginning, once we have a combustion reaction, we're not going to have carbon dioxide and water come back together to make propane and oxygen. But in a reversible reaction, products can react to reform the reactants. And then our definition of chemical equilibrium, and this is a really important definition. So when the rate of the forward reaction equals the rate of the reverse reaction and the concentration of products and reactants remains unchanged. Again, it's really important that we focus in on concentration remains unchanged. The actual molecules are going to be changing because both the forward reaction and the reverse reaction are occurring, but they're occurring at the same rate, so the concentrations don't change. Which actual molecules are in which state, that does change. So again, here's our example, the dissociation or decomposition of mercury to oxide into liquid mercury and oxygen gas. That actually is a reversible reaction that occurs, and we have a chemical equilibrium. Okay, so let's look at, and we have our arrows. When we have arrows pointing in both directions, it indicates equilibrium in a chemical equation. Okay, so we're going to look at a few examples and we're going to look at some graphs. We're going to talk about what's actually happening. So here we have the decomposition of nitrogen dioxide into nitrogen monoxide and oxygen gas. And you'll remember in our unit on kinetics that we always looked at initial rates when we looked at that method of initial rates. And the reason that we looked at the reaction rate at the start was that reaction rate changes as the reaction goes forward, as the concentrations change. And so here we see that we have a reversible reaction. So our nitrogen dioxide its concentration is decreasing as the reaction goes forward. But the nitrogen monoxide reaction is increasing as it goes forward, and the oxygen concentration is increasing as it goes forward. And so we see that we reach this point right about here where the concentrations of them become constant. The concentrations stop changing. And that's how we know we've reached equilibrium. So when we're looking at a graph of concentration versus time, we know we've reached equilibrium when the concentrations become constant. If we were to look at the dinitrogen tetroxide, nitrogen dioxide reaction that we talked about at the beginning, now you'll notice that at the beginning I wrote it the other way, nitrogen dioxide coming together to form dinitrogen tetroxide. Now I've written it the other way. It really doesn't matter. It's a reversible reaction. It's equilibrium. So now you'll notice that my graph is not concentration versus time, but rate versus time. And because of the way that I've written this, you can see that the rate of the decomposition of the dinitrogen tetroxide is decreasing, and the rate of the nitrogen dioxide reaction is increasing. That's because as this reaction goes forward, the concentration of nitrogen dioxide increases, which means that its rate can also increase. And so as this goes forward, both forward and reverse reactions are occurring. Notice that the rate of the reverse reaction initially is 0, but as soon as we start to get some of the product produced, then it can start that reverse reaction. And now we reach that equilibrium point and the forward and reverse reactions are both occurring, but their rates are equal. And so if we're looking at concentration versus time graphs, we recognize equilibrium when the concentrations become constant. If we're looking at rate versus time graphs, we recognize that we've reached equilibrium when the rates become equal. So one last time, concentration versus time, and once we reach that equilibrium point, the amount of each reactant and product remains constant. Again, remembering that that dinitrogen tetroxide is going to continue to decompose into molecules of nitrogen dioxide, but the molecules of nitrogen dioxide are going to continue to react with each other to form dinitrogen tetroxide. So when we're at equilibrium, both forward and reverse reactions are happening. We write those equations with a double arrow. So that's our initial introduction to equilibrium. Let's do a couple of practice problems together, and then we'll start talking about the equilibrium constant and the reaction quotient. So here's our first practice question. I'm going to let you pause and read the question to yourself. And so our question asks us which of the claims is most likely correct. And so if we're looking for equilibrium, we know we reach equilibrium when the concentrations become constant, not the same, but constant. And so we notice that from 155 minutes on, the concentration of X stays 7 times 10 to the negative third, and the concentration of XY stays 4.3 times 10 to the negative second. And so we can logically conclude that B is our correct answer. We don't know exactly when it reached equilibrium, but we know that at 155 minutes, it's already at equilibrium. So somewhere in there, it did reach equilibrium. Okay. So we have another practice problem. We have dinitrogen tetroxide being placed into an evacuated container at 373 Kelvin and undergoing the reversible reaction. And we have a concentration versus time graph. And it asks us when equilibrium is first reached. And so I'm going to let you pause and read the answers to yourself. And we're going to say that it reaches equilibrium at 60 seconds because the nitrogen dioxide and dinitrogen tetroxide remain constant. Sorry, there's an error, a typo in that question, but okay. And one last practice problem. We have this time a particulate diagram, but we're getting the same information. We can count the number of particles in order to figure out what our concentrations are. So it's asking us which of the following is a characteristic of a system at equilibrium that is best represented by the particle diagram. And again, I'm going to have you pause, read the choices to yourself, and then come back. And so we would say that it is C because after 200 seconds, there are no observable changes in the amount of reactants and products, which is a characteristic of a system at equilibrium. Okay, so let's talk about the equilibrium constant, also called the law of mass action. So we're going back to that reaction between dinitrogen tetroxide and nitrogen dioxide. And we can see that that ratio, which we see in this final column here, that ratio of nitrogen dioxide squared to dinitrogen tetroxide at equilibrium remains constant, no matter what those initial concentrations might be, or whether we approach it as nitrogen dioxide, starting with nitrogen dioxide or starting with dinitrogen tetroxide. Larger quantities, smaller quantities, that ratio is constant. So this is the data from those two trials, the last two trials from the table, and you can see this is that same concentration versus time data. but we're only looking at the nitrogen dioxide, so we can see that we reach that same point in both. Look at a different example. We have nitrogen and hydrogen coming together to make ammonia. This is also an equilibrium reaction. It doesn't matter whether we start with nitrogen and hydrogen or whether we start with ammonia. We reach the same proportions of all three substances at equilibrium. It's not necessarily going to be the same amounts, but it is going to be the same ratio. We're also going to go back to that kinetic definition of equilibrium, that when our forward rate is equal to our reverse rate. And so at equilibrium, we know that the rates of the forward and reverse reactions are equal. And we also see that those ratios become constant. And this is where our equilibrium constant comes from. So if we were to write the equilibrium constant, the rate law for the reaction of nitrogen dioxide, sorry, I left out a 2, and set it equal to the rate of the dinitrogen tetroxide, we would find that the ratio of the Ks is equal to the ratio of the concentrations raised to their coefficients. And this is our equilibrium constant. This is our law of mass action, that the ratio of the concentrations of the products raised to their exponent, their coefficients, over the concentration of the reactants raised to their coefficients is a constant when we're at equilibrium. And that is, notice this is a capital K. You'll see it written with an EQ subscript. We'll also talk about it with a C subscript. That just means concentration. We'll also talk about it with a P subscript, and then later on with an SP constant. But in all of them are equilibrium constants. So since this is where our equilibrium constant equation comes from, we do need to think about temperature. We know that the rate constants are temperature dependent. And that means that the equilibrium constant is also temperature dependent. And we saw that when we looked at the dinitrogen tetroxide and nitrogen dioxide reaction at the very beginning, that as we put it in ice or warm water, that changed the ratio of the nitrogen dioxide gas to the dinitrogen tetroxide gas, and it went from clear to dark brown. And so this is that example. So dinitrogen tetroxide, when we add heat, decomposes into nitrogen dioxide. The dinitrogen tetroxide is colorless. The nitrogen dioxide is brown. That's the enthalpy value for this particular reaction. And we know that Kc, or Keq, is nitrogen dioxide squared over dinitrogen tetroxide. Sorry, concentrations of those. And we can see that at different temperatures, those values are going to be very different. So the ratio of those two gases to one another at different temperatures is going to be different. And we can see that right here in that when it is really cold, it's nearly colorless. And once it starts to warm up, then we get that brown color that is telling us that we have more nitrogen dioxide. Okay, so K is temperature dependent. At a given temperature, it will always equal the same value. So how do we write this sort of generically? If we look at this generalized reaction, A plus B yields C plus D, the equilibrium expression is always going to be concentration of products raised to their coefficients over concentration of reactants raised to their coefficients. This is the equilibrium constant. This is the law of mass action. What if we're not at equilibrium? If we're not at equilibrium, we can write the same algebraic expression as that equilibrium constant, but we're going to call it the equilibrium quotient, sorry. Um, so at any point in the reaction, we can write the same algebraic expression. It's not going to have the same value as K, but that's going to be useful to us. Okay, so difference between equilibrium quotient and equilibrium constant is that the equilibrium constant is the concentrations when we're at equilibrium. Equilibrium quotient is the same algebraic expression, but at any point in the reaction. Okay, so we're going to write the equilibrium constant expressions for hydrogen reacting with iodine to form hydrogen iodide, and for, aqueous cadmium ions reacting with aqueous bromide ions to form the cadmium bromide complex ion. I'm going to allow you guys a few minutes. You can pause and write those down, and we'll check them in class. And then we're going to talk about the equilibrium constant when we think about pressure. So because pressure is proportional to concentration for gases in a closed system, we can also write the equilibrium expression with pressures instead of concentrations. But it's really important when we write the Kp, or the equilibrium constant with respect to pressure, that we don't use brackets. Brackets refer to concentration. So we need to write the letter P and then the subscript of the compound that we're addressing in parentheses, and again raised to the coefficient. And while Kc doesn't have units, Kp does. And so it matters whether we write this in atmospheres or pascals. So let's just get in the habit of always writing this in atmospheres. But if we have pressures, we can essentially algebraically use the same expression, but we want to use P and we want to put it in parentheses instead of brackets. And that's where we're going to close for today. And if you have any questions, as always, just let me know.